Hello, everyone. Really great to see this number of people. It really looks full, which is great. So I'm Jakub. Um, I'm going to talk about asynchronous distributed computing. There are some topics that are shared or overlap with what was in the previous talk. So I'll try to take it from a different perspective and to a different ending. So I hope there's not too much overlap, and it's rather good to see these two talks together. Right. The content, there will be three main sections. Introduction. We will look into Python build-ins for concurrency, and then we'll look into how to scale this out. Okay, so first let's just briefly think about what concurrency is. And what basically enables it to you is to do other things while waiting for results, for example. For example, you can wait for multiple calculations. There's a figure that I would like to show. So I guess these people, back in some darker days in Czech Republic, or Czechoslovakia actually, they, I think, were kind of skilled in waiting in queues, and maybe some concurrency would have helped. Now let's think about parallelism. This is more about doing multiple things simultaneously. When we think about concurrency, it usually is aided by parallelism, but it's not a necessity. And examples of parallel computation, GPU vectorized operations, multi-core machines, and this is how a parallelism looks like in a generated picture. You can maybe spot some features of this picture that are not natural for the setting, so it is generated. Right. In base processing, which I try to target this talk to, we care about both usually. We need processes to be responsive, and there we need basically concurrency. If we need to ask the process whether it's doing its calculation, we'd like to get an answer from it. But we also need to process a lot of multiple tasks, usually a lot, simultaneously, and that's where we employ parallelism. So what Python offers in its built-in primitives and library. I will mostly focus on concurrent.futures, which was proposed in 2009. This was already mentioned in the previous talk. And it actually sets a nice foundation on the concepts that other libraries build on and use. There are other standard library modules that are used for concurrent execution, threading, multiprocessing, subprocess, and asyncio, which stands a bit aside. It's a more modern thing. It's so-called cooperative multitasking, and there's an event loop that switches between tasks cooperatively. So it's a bit different take on that. I'll also show how these concepts work together. Okay, let's focus on the abstraction of concurrent.futures. Now, when I say abstraction, if you read the documentation and how we focus on executor, it says executor is an abstract class that provides methods to execute calls asynchronously. Pretty much abstract, I think. So we'll try to a bit understand what that means and go step by step in really exploring how we can deal with concurrent tasks. So for an executor, it usually means we create one, we submit tasks to the executor, we somehow collect results, and then we eventually shut the executor down. It often would kill itself by its own, so we don't usually care too much about it. So let's create one. There's two actually available: thread pool, process pool executors. I think the names describe the classes enough. We either use threads or processes to execute tasks. Then we need to submit. There's now more ways how to submit tasks. We can use submit as a method of an executor. We can also use a map method to do multiple calculations. And then we are now starting to build really the protocol, the concept, how we work with executors and tasks. Maybe a surprise for someone who has not done these kind of things is the result of submit, which is an instance of an object called future. So if we look into it, if we try to print it, it actually says it's a future. It also says something about the state. What is, we can't see in the presentation here, but what happens is you get this future instantly. It does not wait for the execution itself. So future is basically a placeholder that kind of observes the calculation. It gives you access to query the state of the calculation. It eventually gives you access to the result if that result is available. But you need to query it. You need to call methods. The most important ones are result, done, or cancel. So you can even cancel a task if you think it takes too long, or you just realize you don't need it anymore for whatever reason. Right. We can also collect multiple results. If we use the map method, we get a generator. We can iterate over it. I don't want to go into details. It's not the best thing how to collect multiple results, because you need to collect it in order, and if the first one is slow, you need to wait for the others. So there's more flexible ways how you can do it. You can submit individual tasks in a for loop, or just a list comprehension, or actually even use the built-in map and partial. And what you get is a collection of futures, and then you, for example, can use as-completed to iterate over the completed first results. So this now becomes fairly powerful. You just throw somewhere a bag of tasks, and you get basically one by one in a standard Python for loop results as they come. You can also there's also wait, which gives you even a bit more flexibility. You can look at you can basically see in iteration which tasks are done already, and you can use them, and also those that are not done. You can eventually cancel them. For example, if you're fine with just using 5 fastest tasks out of 10 or something. So there's a lot of options you can do with those functions. And then in the end, I mentioned it's a good practice to kind of release resources of the executor. It may or may not be important. If it's a running process like a web server, you would want to release resources. But if it's just the end of your Python script, you don't need to care too much, probably. There's some details of what happens with futures that are already running. So you may explicitly explain what to do for those that I have not finished. There's some non-trivial, maybe surprising behaviors you can encounter if you try to generate random numbers like this. You get not very random numbers, and this is really if you execute it multiple times, you get the same. I also should want to point out we are using process executor, so we would think these are separate processes. There's no state shared, right? But it's not right, actually. There's a state that the processes inherit, and that state is not mutated in the sub-processes, and this is where it leads to. So one needs to be a bit careful sometimes. with these kinds of things. And even if rent in looks like a function, it's actually a method of an object that has a state. Great. There's some limitation, obviously. Thread pool executor, I think the most famous one is the global interpreter lock, which may not be that much of a concern in the coming versions of Python, but still it prevents Python code. And now the Python code is important to mention here to run in parallel, because if the operations in there are either I/O operations or, which is more often the case for data processing, functions written in C or other languages, typically NumPy, Pandas, and so on. These can actually release GIL, and then you can have processes running in parallel, even in a thread in Python. So it's not that bad. It actually can be very useful. Process pool executor. I think the main limitation, besides the quirk that I just showed before with random numbers, is serialization. You need to send objects between processes. For example, if you try to send a lambda function, the built-in executor would not be happy with that. It cannot serialize it, and this fails. Right. What can we do with serialization issues? For example, we can use libraries like CloudPickle or Dill. They are not that easy to fit into the built-in executors, but there's one project from joblib actually that also is a library that was mentioned already, which is like quite a straightforward replacement for process pool. It has some other nice features, including using a specific serialization library like CloudPickle or Dill. I think CloudPickle is the default, and this library will enable you to serialize much more objects. Not everything is serializable, but most of what you would like to be serialized is with these libraries. Now, I mentioned async I/O, and what I think is the most important property of concurrent futures, executors, asynchronous parallel processing is some kind of collaboration with async I/O. And there's one thing that is a bit maybe misleading, because async I/O also has futures, future class, which is to a large extent similar to concurrent futures, but it's not the same. You can't exchange them. You can't evade concurrent futures future. But there is a compatibility layer that you can use. You can create one future from the other by rep future, or you can also have use the run in executor method of loop instance, and this kind of streamlines running something that would be blocking the async I/O loop in a thread or process or even remote cluster. So I think generally you can have async I/O application code, and this can unblock you from the standard limitation of async I/O not being able to effectively multitask CPU instance operations, for example. So let's see what are examples for using the built-in concurrent futures, or maybe the low-key executor. You can really quickly batch processing, do a grid search in a couple of lines. Would be fairly similar to what was shown in the previous talk, just a bit different syntax. we actually saw how it would be done, these. What I mentioned with asyncio, non-blocking data processing, especially if it's not too large, you can have, say, web server, let's say fast API, asyncio native, and then if there is some a little bit longer CPU intense task coming, you can keep the server responsive, but just offloading the calculation into a thread or a separate process. What you should care about is resources always. If you have too many processes and you just fill them, your memory can, of course, get overloaded, or you run out of CPU or something. Okay, and this actually brings us to the last section, which is how to scale these calculations. I will mostly talk about a library called Dask. I will shortly mention Ray. The intent here is not a comprehensive comparison of these frameworks. There are even others, but I think it showcases how these frameworks land and use the concepts from the built-in library. So if you get familiar with those, you can transition smoothly to libraries like that. And also, if you don't work for Qminers, you don't have the nice libraries that they have here. So you kind of left with what open source offers. Okay, so scaling out, what happens at some time? Often you need to process huge data sets. There's heavy calculation for whatever reason, a lot of repetitions. The symptoms usually for memory, you would see your code being killed or out of memory kills. Somehow, it explodes. In the better case, it just stops your Python process. It could be worse behaviors. Or if you run out of memory, if you consume too much CPU, the calculations just are taking too long, and eventually you start to hear your computer fan, which you haven't been aware of until that point. And this is where frameworks like Dask or Ray can help. The very simple figure on the right-hand side shows you how it works, the general architecture. The client, the code that actually calls and wants to do the calculations, talks to a cluster, an abstract one. Usually there's some scheduler and workers who actually do the work. The implementation can obviously be from something very simple to something very sophisticated, spanning multiple clouds all over the world and still being behind a single scheduler endpoint, so you can be scheduling your jobs across the universe. So before you start doing it, just maybe go through a checklist like this, because you're going to spin up a cluster. It's going to cost some money. Even if you don't pay, there's some usage. Someone needs to pay with money, with I don't know, resources, bitcoins, whatever. So try to think whether you can optimize your code. Look into profiling your code, save some memory, CPU. There's a good chance, if you have not done this exercise yet, there could be a lot of savings in resources you need. You can also do some tricks like there's a big data, so you can map files to memory, so increase your memory can still be good enough to process the data, or just process data in chunks. Also, a good thing is if you think already you need to move to Dask or Ray, they can also help you even without scaling to big machines. They can help you with, for example, the batch processing and other stuff. So what these these two libraries are Dask or Dask distributed. These are exact quotations. So they say it's easy to set up, just a Python library, and powerful, providing scale, unlocking complex algorithm, and they also claim it's fun. That's, I guess, up to you when you start using it. Sometimes it's fun. Sometimes you know, hitting whatever part of your body to whatever part of your computer. Maybe you've heard about Dask for its data frame like Pandas API, which is really powerful. This API actually stands on what I'm going to show, the futures API. Then we have Ray, again an open source framework for scaling. They focus, I think, much more on AI. They even have it in the description more, and provides a layer for parallel processing. It's in many aspects it's similar to Dask, at least the let's say low-level concurrency the scheduler part. This is where Ray cores sits, but then Ray, I think, focuses more on AI workflows, while Dask is more tailored to data frame like processes, and that's the applications. But they build. I think that when I follow what they build, they usually bring similar features as the other one did last year, that the other library would develop this year, and so on. So let's look into the API. This is where you can find it's really similar to concurrent.futures, and you would see the API is even called futures, I think, or at least in the documentation they call it futures. You would have a client. The client is not executor, but I'll show how it is similar and how you can actually really swap to use the exact same API as the executor. But you have submit. You can use map, which is a bit different to the executor map, but probably more useful. There's also this really compatibility layer, so you can get. The future is the incompatibility layer. There is a future, but again, there's a third future already. Not sure if we have three futures. Maybe it's good to be able to choose from a couple of futures. It's a kind of superpower. But anyways, the Dask future is not the same as the built-in future. But there is a compatibility layer that gets you an executor that then yields, obviously, the built-in futures. What that means is, if you have an application that uses the built-in futures executor API, you can swap it. You can use this one, the compatible one, without any changes in the code. It would just work. So there's the decision points. You can either profit from specific features or profit from the full compatibility. Again, it integrates with asyncio. Sometimes maybe even more straightforward. I think this is nicer than the built-in library, and I'm actually not sure why the built-in futures are not available, because the Dask ones are, if you turn on asynchronous true at least. Okay, a bit more practical upgrades that you get. I think the most important ones, really. You get data, distributed data, and locality. So when you have big data, you need, or at least you should probably care about not moving them too much back and forth. The serialization, the network can cost time, CPU power, and so on. So you can instruct Dask to store data in the cluster, And also, Dask schedules the jobs close to the data, if possible, so that it sits in the worker memory, and if the worker can execute a task, and or if there's multiple workers, it would pick the one that has the data already, for example. It also has first-class task dependency, so you can pass futures as inputs to calculations. This you can't do with the built-in concurrent futures, and this future somehow magically becomes the real object in the function that's behind the task. I hope it will become a bit clearer when I show an example. There's also support for dynamic or nested tasks. This may be a bit even similar to DAGs. But if you think about what can happen if you submit a task or job from within a remote job, it can actually get stuck, because if there's a single worker which is given a job, and that single worker now asks to find a worker to do another job, if the worker is not smart enough to realize that it needs to free itself, there's no worker to do the work, and it just gets stuck. So there's a way to resolve it. There's also resilience, so that it somehow retries and recovers from some failures. And there's resource management. You can assign workers resources like GPUs, CPUs, memory, and the scheduler would track these resources and distribute jobs appropriately if only when there's free resources. Right. The second time I'm going to escape the camera. No. Okay. What I hope I'm going to show you here is a simple example. I've started a local Dask cluster here. It's not. It's very straightforward, but you can imagine this could be a remote big cluster. But let me show you this short code. What I'm trying to show here is there's a task called load data. I'm artificially sleeping to pretend these functions do some work, but they just sleep. So, but I think you will hope you understand that I don't need to spin too difficult calculations for this demo. There's a couple of functions. And why are they there? There's this layers of how they start here. I want to find out in the NumPy array which the elements that are divisible by another array of divisors, and I explicitly say that I want to do it in chunks. And this is how I do it with Dask. I get this worker client, which is the client that is able to avoid the locking I mentioned before. Now this is a standard NumPy code. I split into chunks, and I map in a list comprehension the check divisibility function. So this call here would be non-blocking, and then I collect the results. You can see that this is a blocking function here. This would be already a list of NumPy functions, and then I just concatenate it here. What I do here is then check the divisibility is here. hope I thought I had a showcase of where a future is actually passed to another function. Now I don't see it. So I'll just show you how it runs in the interface. What's actually in this code, it's downloadable if you want to inspect it, but it's not very spectacular. It's really just to show it works somehow. There's also errors thrown randomly here and retries here, and I also use the resources when I submit. I specify that each task needs one GPU. Okay. So this is the Dask dashboard. If I refresh it. We'll run this code now. You can see in real time you would be able to see the tasks being executed. There's 4 workers. You can go a bit here, see what these are, and then Dask offers you some extras like it can show you the profile of all the functions. So it does profiling for you, an overview of workers. This is the status. This was the previous call, and there's more. So there's sometimes, especially for debugging, useful features. Because when you go into really distributed remote computing, any debugging becomes really difficult very often, and any tools that are available to you that can help with debugging are extremely useful. And let me summarize this. What we've seen is we went through Python built-in concurrency abstraction, especially concurrency futures. We've seen what executor and future classes or objects are and how to work with them, how to couple or use within asyncio applications quite seamlessly, I would say. And then we explored distributed computing libraries, Dask, not so much Ray, but it would be similar in how the code is organized. And we mentioned the enhanced features and properties that they bring to help you scale to distributed, help you tackle pickling problems, efficient data communication, task dependencies, resilience, resource management, and more. And with this, I think I can open this talk for questions. Thank you.